Okay, gonna run it. I'm gonna make sure in my file settings and event and exceptions that I'm breaking on C++ exceptions and not just breaking on the second chance exception, because that means that if the exception is handled in my code, which it is, my debugger won't be notified of it. But I want to be notified of them, not just on second chance. So I make sure that's set, and I'll just resume execution. Okay, seems like there's an invalid pointer dereference. So what you'll see here is that it's accessing address 0x28, and it's getting that address by appending an offset of 28 in hex to RCX. So RCX is going to be a null pointer here, right? If I dump RCX, it's null. So the question is, why is it working with a null pointer? Well, let's take a look at this wait for init function and see what RCX is. If I go to wait for init and see where arg1 came from. Now, where is this called from? This is called from register log query. So we can jump there. arg1, it's arg1 of register log query, which that arg1 to register log query is gservice. And gservice is a global. Since we haven't initialized any globals, we're just calling the internal function directly. This global has not been written to yet, which means it's initialized as 0. And we can prove this. So this global, which is used, lives at offset 1B8A60. So in my code, let's go in my code here. Let me define it. I'm just going to say, actually, I don't need to worry about it. I'm going to do it in init. So in init, I'm going to say uint64 pointer gservice equals to uint64 pointer and an offset. And that offset is going to be the offset of gservice, which is 1B8A60. So this address holds a pointer, right? Because this is a global, which is going to be 64-bit value. You can tell because it's A60, and then the next entry is A68. So that's 64 bits or 8 bytes, and it's a pointer. I'm defining it here, and I'm going to print out the value of this pointer. gservice is %LLX, and I'm going to dereference gservice to print out its value where it's pointing to. This should probably be a pointer then, because it has the address of a pointer. So you dereference this once and you get the pointer value here. You dereference it again and you get the actual contents. But for our test case, we don't actually care about that. We just care about the pointer value itself. So now that I have that, let's compile it. Let's run it. You can see gservice is 0. So the value is 0 of the pointer, and that's being dereferenced, and that's why we have an exception. So we need to either avoid this code or initialize gservice. If I want to initialize it, I need to see where it's initialized in code, which means I need to look for writes to it. If I look through the cross references to it, I can see one write to it here, where it is set to rx1. Now this happens in the function global initialize, which makes sense, right? But even if we have a couple options here. One is to just try calling global initialize and hope that that works. The other is to write a valid pointer to gservice ourselves, which we could do. If I look at gservice, it gets set to rx1. rx1 is first allocated to a fresh buffer of 0xA8 in size, and then it's passed through to the event service constructor. So we could do that ourselves, right? We could allocate 0xA8 to a memory address, pass that to the constructor of event service, and then write that pointer to gservice. Like that would work perfectly fine. Or we can just call global initialize and see if that fixes things as well, because that might do additional things we wanted to do. So in this case, I'm just going to call global initialize. So let's create that function pointer. Type def void fast call pointer underscore global init. It takes no parameters and we're good, right? Takes no parameters, returns void, we're good. Now let's define that as a global. So that f global init, and then that f global init will assign to an actual proper value. So I'm going to assign it here equals to underscore global init, and the offset we're going to use is 54FA0. And now I'm going to do the printf again right after we call f global init. Right, so I define the function pointer, I call the init function, and then I printf gservice again. Let's try that. Okay, so gservice is 0, we run init, and then gservice gets sent to a valid pointer value. And this time we don't crash, but we do get an error result, right? Because 0 was success, non-zero was an error. So we're getting an error. I don't need these printfs anymore. And what I'm going to do now is I'm just going to step through it again in the debugger. I'm going to put a breakpoint on the X entry. Then I'm going to put a sxe ld revt service.dll line, which will give me a breakpoint when that DLL is loaded. Now that that DLL is loaded, I can put a breakpoint on revt service, bang, and the start of where we're going to be analyzing, which is going to be evt rpc register log query, which is at offset 38820 plus 0x38820. Okay, we've hit evt rpc register log query. I'm going to step through it and see how far we get before it exits to return an error. Okay, we're going to register log query. Nice. Going to wait for init. If I go into there, it returned an error. Oh wait, hang on. No, it has not yet. And we continue stepping through. The debug is having a problem. I'm going to take note of this line. I'm just going to quickly restart. Okay, let me put a breakpoint on where we left off at. Okay, continue. Interesting, it dies there, but because the debugger is having an issue there, what I'm going to do instead is I'm going to step through till we get to that function. Continue on, and I'm going to step over wait for init. Alright, I can see that wait for init never actually returns. It raises an exception at this offset. So I'm going to grab the throw exception line here. I'm going to subtract that from the base address to get the offset of where the error occurs. And I'm going to navigate to that offset. So that exception is thrown here. And the only way we can avoid this exception block is if we return out before then, which would be here. And we only return if this value is set to true and this value is currently not being set to 1. And what's happening here is this value rbx comes from arg1. So this is arg1 plus 0x28. And here it checks if arg1 plus 0x28 is 0. If so, it goes to this wait line. So because this is meant to be run in like a multi-thread environment with like one thread doing server stuff and the other thread handling RPC requests and, you know, things like that. This may be here for perhaps, you know, to like synchronize some things or something like that. And because it's waiting for something to be signaled and there's no actual other thread running to signal anything, it's never actually going to be signaled. So it's never actually going to succeed or, you know, get the result it's expecting. And that's why it goes through the error path. Even the name wait for init kind of gives you that hint that it's waiting for something, right? But there's no other thread doing anything for this to like wait on. So it makes no sense for this to be called in our fuzz context. And actually this function doesn't do anything interesting, especially since we aren't running in that full multi-threaded service executable environment. We can kind of just completely ignore this function. There's nothing happening here that's interesting at all. We're just going to hook it out. That's kind of the easiest way to get by this. So we're going to hook out wait for init. We're going to type def it returns void and takes in one argument. So we can type def that pretty easily. Go here. I'm going to call it first, let me do, what is the argument? Oh, it doesn't matter what it is. It is underscore wait for init. Define it as a global. F wait for init. And then, of course, set it to a valid pointer. F wait, well, actually, I'm going to be using it for hooking, right? So I'm actually going to have to define that a little bit differently. I'm going to define that similar to how I defined the RPC impersonate client call. So this is going to be void. In API, it's going to be f wait for init. It's going to take just a car pointer, works as arg1. Now here, I'm going to copy this line. This is going to be, instead of hooking RPC impersonate client, right, we're doing f wait for init, which returns a void and takes the car pointer. And the address, we're not going to get from getproc address. We're going to get the address as an offset of the revt service binary. And that offset is going to be 387D0. And then we're going to replace wait for init with my wait for init. Okay, so that's the hooking there. Let's do my wait for init, void my wait for init, car pointer arg1. What do I want to return? Well, actually, wait for init, when it's called, the return value of it isn't actually used. So And it is marked void after all, so we return nothing. We just return. Now that that is hooked appropriately, let's try running it again. Oh, it works. It even says res is 0, which is success. So it seems like we got it working. I'm going to verify this with procmon quickly. So let me run procmon. I have a filter in procmon to capture anything that relates to the myevtx file. Let's run the code again. And ooh, do I have read files filtered out? Yes, I do. Let me fix that up. And let me run that again. Okay, now we can see read files happening. We have an 8-byte read file, which occurs at determined file type under getLogObject, as expected. We have a 128 read happening in getLogObject, open external log, get file, open file, read file header. And then we have additional reads, 3 extra reads. And these reads don't happen under getLogObject. They happen under register log query, build complex query, and query. That query is a vtable entry depending on what log object was opened, and then that reads extra data from the file. So now that we're harnessing EVT RPC register log query, we're able to reach these additional reads. Now we could take this further. If you looked at the procmon trace when we double click an EVTX file, so let's compare that quickly. If I double click the EVTX file, let me remove some of these entries we don't care about. There was additional reads, right? Like this long read. I'm just waiting for procmon to download the symbols. Now this doesn't happen under registered log query. It happens under EVT RPC query next. Now, if we wanted to harness this function, this one's actually defined as well. In fact, it's right here linked to already on MSDN. EVT RPC query next. And some of the inputs, like the p context handle log query input that it takes as argument 1, is actually one of the outputs that we get from register log query. So now that we can successfully call register log query, we can continue in harnessing query next, which would reach these additional reads on our input. And with that done, I think that covers all the read files that we've seen on our input. But before we get to that, or before we could even look into that, we need to make sure that we can fuzz what we currently have. Because right now we know that we can call it successfully, but we haven't tried fuzzing yet. So let's give that a shot. I'm going to remove the printfs because we don't need them for fuzzing. Let's see how this code goes while fuzzing. I'm going to recompile it now. Okay, I've got WinAFL here, and I have a sample command line. Now, in this sample command line, I'm getting my inputs from a folder where I've got the EVTX file. I've got an output directory, pointing to DynamoRio, getting coverage from RevD service. Our target method is fuzz, which is correct, and nargs is 1 because our fuzz takes 1 argument. Looks good. Let's try running this. We can see that it's nudging processes, and you can actually see why this is happening if we look at procmon. Actually, I'm going to have to change the filter to add in the case where the path contains car underscore input, because that's going to be part of the file name RenAFL uses, I believe. Okay, now I can close this, and if you don't want it to use car input, you can also provide -f and then a file name like evtx.evtx, and RenAFL will use that name instead. But what we can see is that, see these errors, sharing violation. What's happening is, whenever a fuzz case happens, right? This does the parsing, and then as soon as it goes to return, RenAFL patches the thread back to the start of the fuzz loop, and it replaces the evtx file or your input on disk with the next input, which means it writes to that file. However, what's happening is that our fuzzing code is opening a handle to the input and reading the input during its fuzz case, but it's not closing the handle. And because the handle doesn't close, when AFL goes to overwrite that handle with the next input, or the file, with the next input, it can't get a handle to it because it's opened exclusively in our target. So that's a problem. When AFL, you don't have this sort of issue with like shared memory stuff or like with memory-based fuzzing, because you don't typically hold a lock to that. But with a file on disk, RenAFL can't replace it if this register log query function keeps a handle open to it even after we've returned out of it. So there's a couple ways we can handle that. I'm going to go through a generic kind of quick way that works in this case, but you can kind of tackle this however makes logical sense to you. Whether you want to find out where the log file is actually opened and make sure you save off that specific handle and close it, or do something else. In my case, we're going to actually hook nt-create-file, which all the create-file APIs go to, whether it's create-file W or A or nt-create-file directly. We're going to save off the handles that are created during the fuzz case, and we're going to forcibly close them all. But we can't just call close handle on all the handles, because that handle may already have been closed. So we need to check that the handle is valid first. So this is what we're going to do. I'm just going to type it up here. 1. Hook nt create file. 2. Log all open handles. 3. Close all handles at end of test case. 3.a. Ensure we validate handles before closing. And that's because in this case, we're not hooking close handle, which means while we log a handle that's opened, the target may have closed that handle. And since we're not logging close handle, we don't know that. And if you go to close a handle that is invalid or already closed, that may crash the program. So we need to have some way of making sure it's a valid handle first.